Okay, good morning everybody. Welcome to last lecture on mixed signal electronics. Originally we intended to have today a double tutorial, so I didn't make it to finish the Sigma Delta stuff last week, so we will have a short lecture part today, and then Michael will have two tutorials, and will also give you the opportunity to ask questions regarding the exam and to discuss stuff which was unclear. Okay, so last week we discussed about the Sigma Delta modulator, and we saw that we can start with a first order loop. This was something like this. We had a basic discrete integrator, which was normally a switch capacitor integrator, c to the power of -1 over 1 minus c to the power of -1. And the input signal is sent to this integrator. Output signal of the integrator is quantized, in the extreme case with a 1-bit quantizer, and then this output signal is converted back into the voltage domain and subtracted from the input signal. So here we have a DAC. This DAC is often not drawn, but if you assume that this is here really a bit, then of course you have to translate this back into the voltage domain in order to subtract it from the input signal. We saw that we can have here a transfer characteristic which says that the output signal is the delayed input signal, c to the power of -1 of the input signal, let's call it u. So this is the input signal. And we have seen that we add a quantization error here in this quantizer. We model this simply as an adder that adds the quantization error E to the output signal of the integrator. And then we had here this first order noise shaping term, 1 minus c to the power of -1, first order numerical derivative of the quantization error. And then we saw that this noise shaping term pushes the quantization noise out of the band of interest, and so increases the signal to noise ratio dramatically. And we saw that we can increase the signal to noise ratio even more if we go to a higher order noise shaping, and higher order noise shaping meant that we had here not 1 minus c to the power of -1, but that we had this term to the power of 2 or 3. We saw that it is ideally possible to have second order noise shaping, and then to go for third order or higher order noise shaping. We saw that there are two problems occurring in the loop. The first one was that there is a risk of instability of the loop, and that the signal and the noise transfer function is not ideal anymore, that there is somehow a distortion in the transfer characteristics. And this comes from the fact that in order to keep the loop stable, we have to choose the coefficient such that as a side effect the signal and noise transfer functions are not ideal anymore. So the question is, how can we build a higher order Sigma Delta modulator without having the risk of instability? And therefore we can say here in this circuit, if we take this signal, this is the output signal. This is, let's say, if we have here an auxiliary signal, call it H, then we have here at this term, at this terminal, or here we have H plus the quantization error E. So if we then take the signal H directly, then we can subtract this H from this signal, and at the end we get only the quantization error E. And the idea is now to say, okay, let's take this quantization error, put it also into a A to D converter, also into a sigma delta modulator, in order to measure this quantization error and compensate the result of the original sigma delta modulator. And this is the idea of the so-called cascaded sigma delta modulator, or people also say this is a mesh structure, where mesh is, it's the right one, where mesh is the multistage noise shaping sigma delta modulator. Here you have exactly what I have drawn so far. This is the first order sigma delta modulator. You take the signal which contains the quantization noise, and you take the same signal without the quantization noise, namely the output of the integrator, you subtract this, and then you get the quantization error of the first sigma delta modulator. So here you get a quantization noise signal E1. And this signal is then fed into a second sigma delta modulator, and this second sigma delta modulator adds a second quantization noise E2 here. So what is the output signals? We know that the output of the first sigma delta modulator is Y1, given by the delayed input signal, which is C to the power of minus 1 U, plus first order noise shaping term 1 minus C to the power of minus 1 times E. The output of the second stage is Y2. This is the delayed input signal. So it is C to the power of minus 1, and the input signal now is the quantization error of the first stage. So this is E1 plus a first order noise shaping term 1 minus C to the power of minus 1 times E2. Let me write these two equations above each other, so we can say we have a Y1 equal to C to the power of minus 1 U plus 1 minus C to the power of minus 1 E1. Sorry, this is E1. And we have a second term, which is Y2 equal to C to the power of minus 1 E1 plus 1 minus C to the power of minus 1 E2. And if you look at these two equations, you can see that we can get rid of the quantization error of the first stage if we multiply the first term by C to the power of minus 1 and the second term by 1 minus C to the power of minus 1. And if we then subtract these two equations, then you can see that this middle term, depending on E1, cancels out exactly. And what we get is that we have a Y given by C to the power of minus 2 the input signal U minus 1 minus C to the power of minus 1 squared E2. And if you look at this, then you can see that we have exactly the behavior of a second order sigma delta modulator. We have here our delayed input signal, and we have a second order noise shaping term. So you might say, well, this is what we already built with the second order sigma delta loop. So why implementing a second order sigma delta modulator like this? And you are absolutely right. It makes no sense to make a second order sigma delta modulator like this. But you can of course do this with higher order. You can take two second order sigma delta modulators and combine them in a similar way to achieve a fourth order noise shaping, or you can combine a first order and a second order sigma delta modulator in order to achieve third order noise shaping. What is missing here so far is how to implement these two, or the combination of these two equations. And you saw that it was necessary to delay the first output signal y1. We multiply this by c to the power of -1, which means that we have to insert a flip-flop here which delays the signal by 1 clock cycle. And we multiplied the second term, which means the second output, by 1 minus c to the power of -1, which is 1 minus c to the power of -1. So what we do here is that we take the original signal and subtract the delayed signal. And then at the end we subtracted these two equations, so I have to take this signal, and I have to put it to a digital adder where I can subtract the two signals, and at the end I get my signal Y. Interesting here is that you increase the word width by this arithmetic. So we have 1-bit signal here, we have a 1-bit signal here, and by the arithmetics you go up with the number of bits. So it depends on how you represent these numbers, but for sure you have here something which is 2 bits. And of course you will have something that is 3 bits here. Can be even more if you code it in a different way. But you see that this post-processing brings the increased accuracy, and therewith also increases the word width. Okay. This diagram have you seen last week, and here was one line which you didn't understand so far, and now you understand what cascaded modulator means. In this case, there is a cascaded modulator of 3rd order. This means that it is a modulator that is exactly built like this in its multi-stage structure. And as I already told, you can of course use a multi-stage structure also with different components. So here you can see that we have a first stage consisting of a 2nd order sigma delta modulator, and you have a second stage consisting of a 1st order sigma delta modulator. And honestly, I have, okay. Well, you should analyze this structure at home to exercise what I did for this modulator here, that you exercise this for this modulator in order to get a feeling and understanding how to combine several modulators in order to achieve higher order noise shaping. So of course you will need some logic here, and you will need some logic here, and then you have to combine these two data streams in order to get your final output. And I want to know what you have to put in here and here. Okay? Very important exercise. Good. Another point is the so-called scaling of the sigma delta modulator. You know, we have a nonlinear element in each sigma delta modulator loop, and this is this comparator. And the strategy is to have only the comparator as a nonlinear element. If you have a very high input signal for a considerable time at the input of an integrator, then the output of an integrator goes up and up and up. And as no operational amplifier is ideal and has unlimited output voltage range, somewhere it saturates. So what you will see is first that you run into the nonlinear gain characteristics of the operational amplifier, so you have nonlinear distortion, and if the output increases even more, then you really clip and saturate. And then of course you have strong nonlinear distortion in your sigma delta loop, which is not desired, because then all the theory collapses and the transfer behavior is not as expected. On the other hand, it is not acceptable to have only very small signals, because if the signals are always very small, so for instance, if you say, okay, all my signals are less than 10 millivolts, then of course the ratio to the noise power is also weak, and you cannot get a good resolution because the noise dominates. So what you want at the end is that you have signals that are considerably high in order to get a good signal to noise ratio, but that are small enough to avoid a saturation of the operational amplifier. So this is at the beginning not guaranteed in a sigma delta modulator. So the question is, how can we assure that no saturation occurs? And therefore you can again use your MATLAB model and say, okay, here in this example we have a second order sigma delta loop, and then you put representative input signals at the input of the sigma delta modulator and simulate for a while. So in this example I put a sine wave at the input of the operational amplifier, and I logged the data at the output of the first integrator and the second integrator. So huge amount of data here, and then you put this data into your MATLAB and plot a histogram. And then you get here two histograms, and you can see the output or the signals occurring at the output of the first integrator look like this, and they are between minus 2.5 and plus 2.5, and the signals at the output of the second integrator are between minus 3.5 and plus 3.5. This is only an example. Okay? Then let's say that our operational amplifiers would saturate if the voltage is larger than plus minus 1. So we can see here, of course, as the signals are much higher, and also here, both of these integrators will saturate. So we have now to find a strategy to avoid that these guys saturate. And this strategy cannot be that we say, okay, we simply use a higher voltage, because this is usually limited by your technology. So the max values are given by your circuit technology and by circuit topology and by technology, so we have to look for something else. So what we can state here, except of this element, everything is linear. So we can use linear transformation of this circuit. And we can for sure say, let me go back here. If I scale this signal here by 1 over 3.5, then I also scale the output by this factor. So if I scale it like this, then the signal at this point is bound to plus minus 1. In order to compensate for this, I can say, okay, now I add a gain element here, which is 3.5. Then everything looks the same. Nothing has changed, except the fact that the signal here at the output of the integrator is now limited between plus minus 1. Okay. Then I can continue and say, well, here I only look at the sign. This is a 1-bit quantizer, so I can neglect this one because scaling this back would not change the sign, so I can neglect this one. And I can say, well, I can shift this gain element to this point and to this point. And then you end up with something like this. You have here your 1 over 3.5. You have here your 1 over 3.5. And at the end, at this point, you get output values according to this histogram, and you can see that this is inside our limits. Okay. Next step is to have a look at the second integrator. Here, this guy is between plus and minus 2.5, so I can insert here a 1 over 2.5, and here a 1 over 2.5. And here I have to compensate for this now, which is x 2.5. If you look at your Sigma Delta at your switch capacitor implementation of the Sigma Delta modulator, then you can see that the coefficients are actually not amplifiers but corresponds to the ratio of the capacitors in your switch cap circuit. You know, you have your input cap and your feedback cap, and the ratio of this determines these factors. So at the end, you end with a structure like this. You can combine these factors. This reflects in the ratio of your caps, and you have output signals that are limited in between plus minus 1, so there is no saturation in your amplifiers. This is what people call scaling of a Sigma Delta modulator. Okay. What is the main question you have for this chapter on oversampling A to D converters? Well, the main question hopefully is how to build an analog to digital converter out of this. Sometimes I already used the term Sigma Delta ADC, which was not so correct because what we discussed so far is only the Sigma Delta modulators. And indeed, we have something that creates a high frequency bit stream, but nothing that corresponds really to a AD converted signal. So what is missing actually is the post-processing of the Sigma Delta modulator signal. To build a complete Sigma Delta modulator, we need, of course, what we need in each ADC, an anti-aliasing filter and a sample and hold element. And then we have this Sigma Delta modulator that we discussed so far. And this Sigma Delta modulator was a device that took the input signal and translated it into a high frequency bit stream with very low resolution. So we have here a low word width. And we have a high bit rate. Or let's say a high sample rate. If you think about digital signal processors, then this is devices that work with a moderate frequency with a wide width. So this is not devices that love to work with 1 bit wide signals that occur with an ultra high frequency. So there is something needed that translates this bit stream into something that has a larger word width and a lower sampling frequency. And this is what we have here. So assuming that we go in here with a 1-bit signal, then we put this to a digital low-pass filter, and the output of the digital low-pass filter then may have n bits. And the digital low-pass filter has the purpose to remove everything that is out of the band of interest. So remove outside the baseband. And this means that we remove most of the quantization noise. Okay. And if this quantization noise is removed, then we can reduce the sample rate without the risk of aliasing. So what we do here is that we go from the high sampling rate Fs to a low sample rate, for instance the Nyquist rate or something slightly above. How this works can be seen here pretty well. Assume that you have an analog signal, and this analog signal corresponds to such a spectrum. Then you sample and hold the signal, so you get here in the time domain this step function here, and you get then in the frequency domain your original signal, and you get your replica spectra at multiples of the sampling frequency. If you consider also the step width, then this replica are damped. If you take the ideal value, then of course you see here an exact replica. And then the next step was to put this into a sigma delta modulator. And the sigma delta modulator provided a representation of 1 bit in our example, which is plus minus 1. And we saw in our linear analysis of the sigma delta modulator that the input signal is just delayed, so it's still contained in the output signal. And this can be seen here. So even for the sigma delta modulated signal, you have your original signal and you have the replica. However, what you also have is a huge amount of quantization noise. This is what you see here. And for sure it is obvious that we cannot take this signal and downsample it directly and to reduce the sample rate directly, because you see this signal is not band limited. If I would reduce the sample rate, then this quantization noise here would fall into the band of interest and would overlay my original signal. Hence we cannot do this. However, what we can do is to use a low pass filter, and this low pass filter filters out this part. So what the low pass filter does is to remove this green quantization noise. And then after the low pass filtering, we have something like this. We have the original signal. For sure there is some amount of quantization noise here, but this is very low because the noise shaping assured that in the band of interest the quantization noise is low. And you see of course here the replica, and you see that there is a huge distance between this baseband signal and the first replica. Well, the distance is huge because we still have the very high sampling rate, this oversampling rate of the sigma delta modulator. And you can see it is absolutely not needed anymore that we have this high sampling rate. So now we can reduce the sample rate, so then everything is pushed together. The first replica occurs nearby to the original signal, so it is here. Then the second replica also occurs pretty soon, but everything is fine. Then we have removed the quantization noise in advance, so there is no risk of aliasing doing this. So at the end, if you look only at this signal and this signal, then you have what you would expect from a Nyquist rate ADC. You have analog signal and you have a digital representation at the output with a moderate sampling rate. And please also keep in mind, filtering the signal means arithmetic operations on the signal, and each arithmetic operation consisting of multiplication and adders increases the word width. So you start from a 1-bit quantized signal at the output of the sigma delta modulator, and by filtering you increase the word width, and hence at the end you get a high resolution output signal. If you look at these samples, then you can see this is not only plus minus 1. This is now a real sample with a real highly or fine granularly quantized value. Okay. I want to comment only shortly on how to quantize these, on how to low pass filter these signals. What you can see here is that you have a very high data rate here. So you have to low pass filter this, but the goal is to low pass filter this efficiently, because from here to here you get rid of most of the samples, so you throw away most of the samples. So the goal is to have a not perfectly accurate filter, but to have a very efficient filter for this decimation. So efficient filter for low pass filtering this low resolution but high frequency data stream. And a very efficient filter is the so-called Sinc filter, which is only a moving average of n samples. We will see this soon. So what is done is that you take your sigma delta modulator, then you put it to a Sinc filter, and as the Sinc filter is not a perfect filter and causes some distortion also in the baseband, you do not decimate until your final frequency with this Sinc filter, but let's say to a rate of 8 times the Nyquist rate, and then you use a more advanced filter to do the final low pass filtering. You can also say, okay, I use a Sinc filter, then I use some intermediate stages. Here in this example it's half band filters, because this is also efficient filters where half of the coefficients is 0, and then you have an advanced final filter which may even compensate for the role of the Sinc filter in the band of interest. Depends on your accuracy requirements what you use. But something that you need in each case, and which is very important that this is efficient, is the Sinc filter, and hence I will discuss the Sinc filter. And the Sinc filter is simply taking n values of the bit stream and building the average. So we say the output of our Sinc filter is the sum of the last n values. So we say the sum k equal from 0 to n minus 1 of x n minus k. So we take the last n samples, add them together, and we divide it by 1, or we divide it by n. So we have the average value of the last n samples. Then we can translate this into the frequency domain by doing the C transformation. And this gives us a YC. C transformation is linear, so of course we have the 1 over n. The time shift reflects in coefficients, or in multiples of c to the power, no, in exponentials of c to the power of minus 1. So we have here xc times the sum and we can simplify this sum term, equate it, and what we get is xc over n times 1 minus c to the power of minus 1 minus n over 1 minus c to the power of minus 1. And of course we can also evaluate this for technical frequencies, and then we get x over n 1 minus exponential minus j omega n t divided by 1 minus exponential minus j omega t. Then you can use the same trick we used so often in this course. You can take the root of this and put it in front of the fraction, and what we get at the end is, okay, I have to start here, this is pretty large equation. You have 1 over n exponential minus j omega n t over 2 divided by exponential minus j omega t over 2. And then you have the sine. I go quickly through this because this is a transformation that you have seen several times this semester. So we have here the sine over sine of omega t over 2. And you can write this also as an exponential of minus j omega t over 2 times n minus 1 times sinc omega n t over 2 divided by sinc omega t over 2. This leads to the name of the filter, Sinc filter. Some people call it comp filter. You can also say it's a moving average filter. Important is to understand we take n values and we build up the average of this. We will see how this filter looks like on this slide. You can see here for varying order, so for different ends, how this filter function looks like. So here you can see that we have n equal to 4. Here you can see we have n equal to 32. On the left hand side you see this on a linear scale. On the right hand side you see this on an exponential scale. And what you can see is that even if I average many values, then the damping of this filter is not too good. Okay, so this is also a disadvantage of the Sinc filter, that it is easy and efficient to implement, but it is not good in terms that it has a sharp roll-off or that it has a good damping. You can see here from the peak value, this is what your signal that you want to keep, and here this is the quantization noise that you want to suppress, so the distance here is not too large. You can also see that there is a certain roll-off here, and this is the reason why you may need a more advanced filter that compensates for this roll-off here, because yet the Sinc filter already distorts slightly your signal in the band of interest. Okay. To get around the fact that the Sinc filter does not suppress the quantization noise so strongly, we can cascade several Sinc filters. So we can say, okay, each Sinc filter has a weak damping, so we cascade several of them. And the good rule of thumb is that you say, if you have Lth order noise shaping, then you cascade L plus 1 Sinc filters. And the idea behind that rule of thumb is to say, okay, the Sinc filter has to suppress the quantization noise stronger than it comes up by the noise shaping. So if we cascade several of these guys, then you can see that then, especially in the log scale, you can see that then the suppression here, the noise suppression, is stronger. Okay? However, you have the effort to cascade several of these filters. Good. How to implement these Sinc filters? Well, what we want to implement is a transfer function given by 1 minus c to the power of minus n over 1 minus c to the power of minus 1. So we can partition this and say, okay, this is 1 over 1 minus c to the power of minus 1 times 1 minus c to the power of minus n. So we can say, okay, let's cascade two filters implementing these terms. I hope you recognize the first one. This is a discrete time integrator. So we have here, for the first one, we have the input signal that is passed to the output. Input signal is stored and then added to the next input signal. So we have here 1 minus e to the power of minus 1, and we can say, okay, this guy, this is also quite simple. This is taking the input signal to the filter, taking the signal again, delaying it by n cycles. So we have a c to the power of minus n, and then subtracting the two values. Taking these two building blocks in the digital, implement them in the digital domain, cascading them, this gives your Sinc filter. And then I said we have to cascade several of these Sinc filters. So we have to take L plus 1 of these red building blocks, L plus 1 of these green building blocks. We can change the order because it is a linear behavior. And then at the end, we have a structure like this. So you can see that we have here a cascade of several of these integrators, and we have here a cascade of these differentiators, where we subtract m times delayed signal from the original one. Then at the end, we have to scale this by a factor, because we said, okay, this is an averaging, so we have this scaling factor m here, and we have to downsample it. So which means that here we reduce, or we throw away most of the samples. And always if you have something like this, that you throw something away, then you should start thinking, can this be implemented more efficiently? Can we implement it in such a way that we even do not compute the samples that we throw away later on? And one step in this direction is to say, well, here, until this line, everything works with the high rate. So you can see there is arithmetics, and you can see that there is c to the power of minus 1 elements. On the right-hand side of this, you can see that here we delay by m cycles. So here it is still running on the high rate, because we have not reduced the sample rate so far, but these delays of m cycles show that this is not needed actually. So what we can do is that we reduce the sample rate in the middle. So here we go already down by a factor of m, and then you have simple delay elements here. However, these delay elements are now clocked by the lower rate, namely by the m times lower rate. One thing that you can also see here, and this is something I will discuss in my digital course next semester, is for sure this is a structure that you cannot implement directly, because if you, let's assume we have 10, okay, 10 is much better, let's assume we have six adders here in series, and assume that we come out here with a sigma delta oversampling frequency which is very, very high. Then you can see that we have all these 6 adders in series. So the delay of the adders here becomes critical, and you have to think about pipelining these structures. And of course, you will normally implement these integrators not like this, but you will implement them like this, that you put in here already the pipelining into account. So you put here c to the power of minus 1, and then you feed the signal back like this. And then you have your next stage with the adder and the flip-flop and so on. And you can see now in between 2 flip-flops there's only 1 adder left. So you can you have saved here overhead in implementing very fast adders, or have enabled this structure at all. Okay. Is there questions on the Sigma Delta A to D converter? So what you have to know is Sigma Delta A to D converters is two things. It is the Sigma Delta modulator and it is the digital low pass filter and sample rate reduction element. Okay, we are nearly done. Sorry, it takes longer than expected. The funny thing is, we can use the Sigma Delta modulator not only for implementing ADCs, we can use it even to implement digital to analog converters. And if you look at this block diagram, that it looks nearly the same as the one that we discussed so far. Assume that we come in here with a digital signal. Assume that this is a signal with moderate sampling rate, let's say 4 times the Nyquist rate, and it has a large word width of, say, 16 bits. Then what we do here is that we increase the sample rate. So we come in with the low rate, and now we increase the sampling rate dramatically and go to a very high sampling rate. So let's say we add an oversampling factor of 128. So at this point, we have still the high word width, but with a high sampling rate. We are pretty fast here, but still in the digital domain. Then we can use an interpolation filter. This is a low pass filter. And this one is needed because increasing the sampling rate here first means that we just pad zeros, and by doing this low pass filtering we achieve that we have really high frequency samples of our analog signal. So assume that we have here a digital signal, wide word width, high sampling frequency. And then we put it to a Sigma Delta modulator. And the Sigma Delta modulator translates this into a bit stream, in the extreme case of 1 bit, but with the high frequency. This Sigma Delta modulator is a digital circuit. So if you think back to the block diagrams that we discussed so far, I never said this has to be implemented with switch capacitor circuits. You can implement this discrete time transfer function with switch capacitor circuits. Then you end up with an analog Sigma Delta modulator. One you will need to build a Sigma Delta analog to digital converter. But of course you can implement this discrete time transfer function also in digital domain. If there is written 1 over 1 minus c to the power of minus 1, well, you can implement this exactly as we did it on the previous slide in the digital domain, building it of adders and delay elements. Okay, and if you do that, then you end with a digital Sigma Delta modulator. There's even more efficient ways of implementing such a device, which is beyond the scope of this lecture. If you're interested in this, we have it in the next semester. But the point is, here at this position you have a 1-bit signal with high frequency. So the interface between the digital and the analog domain is only a 1-bit DAC. So you can go from the digital domain here to the analog domain by a 1-bit DAC. And honestly, a 1-bit DAC is a pretty simple device. There is nothing I can imagine to build this even simpler than to translate 1 bit from the digital domain into the voltage domain. Okay? You can say if I have 12 bits, then it's complicated and it's advantageous to go to 1 bit. But 1 bit is really, really minimum effort to build it. And that's also the reason why converters like this is built, that most of the effort is in the digital domain, and then the actual mixed signal element, the interface to the analog domain, is very, very simple. In the extreme case, only a 1-bit DAC. And then we need a low-pass filter. And the low-pass filter, this has the purpose to remove the quantization noise. And in many applications, the low-pass filter is inherent to the system. For instance, if you have an actuator like an earphone or something which is pretty pretty slow, then this element can contain the low pass filter without the need of really building it of devices, but it can be inherent to the actuator. The signals look like this. Assume that we are in the digital domain, have a signal like the dashed line here with these samples. First step was to increase the sample rate. This consists of two steps. The first one is to insert zeros here, and then you have these interpolators which brings these zeros here to the dashed line, and then you have something like this. In the frequency domain it looks like this. You have a signal that is sampled with the Nyquist rate, so all the mirror spectra are nearby, one beside another. And then you increase the sample rate, so you stretch everything, and then you see this is your signal of interest, and this is the first replica. So you separate the replica spectra considerably by increasing the sample rate. Then you put it to the Sigma Delta modulator. The Sigma Delta modulator gives this very basic representation of 1 bit plus or minus 1 and adds all these quantization noise. Then you go from the digital domain with your 1-bit DAC into the analog domain. Then you have essentially the same. You have your signal, the replica, and you have the quantization noise. And now if you use the low pass filter that removes this, then you end up with a baseband signal without the quantization noise, something that is in the digital, something that is in the analog domain. Okay. That's it more or less with the Sigma Delta modulators. I have two comments for you related to more actual developments. In order to go for very high resolution, high signal to noise ratio, it is not the case that people always use only a 1-bit quantizer. There is also devices that are called multi-bit Sigma Delta modulators, which means that you have not a 1-bit quantizer, but let's say a 2-bit or 3-bit quantizer. The point is that then the resolution is of course higher. Remember in your signal to noise ratio formula there was this 6.02 times the number of bits term. However, there is more implementation effort because then you have a more complex quantizer where linearity is much more critical, and you have also in the feedback path you have a real multi-bit DAC which increases the effort of the implementation. Then of course if we implement switch capacitor Sigma Delta modulators, then you know, as in each switch capacitor circuits, between 2 clock cycles all voltages have to settle. And if we in the same moment talk about very high sampling frequencies, then it is clear that somewhere there is a speed limit, because you have to wait after each clock cycle that all voltages internally settle, which means you have to wait for the charge transfer from one cap to the other. This takes some time. So this leads to the fact that at some point the speed of the Sigma Delta modulators implemented in switch cap techniques is limited. So there was a need to go for even higher frequencies, and this was where people invented the so-called continuous time Sigma Delta modulator. In some sense, the continuous time Sigma Delta modulator is a step ahead. In some sense, it's a step back. We will see this soon. The idea is to say we do not have something where the input signal is sampled and then passed to a discrete time filter. Now we have a continuous time filter, an HS, and we sample after the filtering. The effect is that inside the filter there is no switches, there is no switch cap techniques, there is nothing to wait for settling, except the discrete time, the continuous time filtering inside this HS block. And this leads to the fact that we can operate such a device by approximately an order of magnitude faster than we could operate a switch cap circuit. So the idea of going to the continuous time sigma delta modulator is simply speed, or to reduce the power at a given speed. But the idea is that we have here, and this leads to the name continuous time sigma delta modulator, that we have here a continuous time filter. However, you can imagine that this brings some disadvantages. So we said, for instance, that the switch cap technique is so good because it is robust against variations, because we always had this ratio of caps. Well, if we have here, let's say, RC implementation, then we end up with all the trouble that we have with RC circuits. So this is more susceptible to variations. You can also imagine, if this is a continuous time integrator, then this guy will check the input but also the feedback path at any time. And if we switch here the input of the DAC and there is some glitches or some noise or something that is not ideal, this guy will see it and will take it into account during the integration. And hence, in some sense, such a modulator is much more difficult to design than a switch cap one. I have you this table in here that summarizes this and compares the continuous time with the discrete time sigma delta modulator. Let me go quickly through this list. The first aspect is the anti-aliasing filter. Well, in the discrete time, you sample at the input, so you have to assure that no aliasing occurs. So we need an anti-aliasing filter there. In the continuous time, you may omit this one, because here we have also something like a low-pass filter. The integrator has also low-pass characteristics. So we may omit a dedicated anti-aliasing filter because we sample here, and this one can serve as an anti-aliasing filter. Well, I already said that the sampling is done now inside the loop in the case of the continuous time sigma delta modulator, and there is a benefit because sampling errors are injected at the comparator, and this is the point where the noise shaping is effective. So sampling errors are subject to noise shaping, which is good. Regarding maximum frequency, well, this is the reason why to go to continuous time. The speed is relaxed in the continuous time because we do not have the switches and we do not have to wait for the time constants in the switch cap circuits, and hence we can operate this normally 5 to 10 times faster. The jitter is critical because this is what I said. Everything that is not ideal here and varies here is seen by the integrator because this one works continuously. So if I shift something here, well, then I see this in the integrator. In the switch cap circuit, jitter is only relevant at the sampling element. But once in the discrete time domain, if I wait long enough for settling, then the jitter is not critical. The same holds for the loop delay. The loop delay becomes visible in the continuous case, well, because the integrator is active all the time. Switches is an issue in the discrete time domain. The switches cause some noise. The switches are the root cause that we have to wait for settling. So this is a disadvantage here in the discrete time case. In the continuous time, there is no switches. However, there is also elements that are more critical in the continuous time case. For instance, the comparator. A comparator has a delay that depends on the value of the input signal. If the input signal is very, very small, then it takes longer to take a decision than if the input signal is very large. This is not an issue in the discrete case because I wait anyhow, but it is an issue for the continuous time modulator. Okay. The feedback DAC, well, the waveform that occurs while switching the DAC is of minor interest for the discrete time integrator, because we wait until it has settled. In the continuous case, it is an issue. Process variations, this is I already have commented. And finally, the noise generation is worse in the discrete time integrator. Well, this is because of the switches. If there is switching activity, then we always have some noise injection due to the switching. If there is no switches, we don't have this noise component. Okay. That's it with mixed signal electronics, the content that we have planned for this semester. So I really hope you had fun with this course. I really hope that you learned something. I got pretty different feedback. Some people thought it is too easy. A few thought it is too difficult. So give us feedback if you have something that you liked a lot or did not like at all, so we can improve year over year. So of course this is no benefit for you guys, because I hope that everybody passes the exam, but it is a benefit for future student generation, and I would highly appreciate to get feedback like this. So if you see some unnecessary overlap to other courses and stuff, please flag this, and then we can discuss it and try to improve. So our strategy is always to improve and get better year by year. Okay, this is what I already mentioned. Analog for automotive and mobile communications. This is, let's say, advanced analog course next year. Pretty interesting. And this is my course for the next year, where I would say this is something in between mixed signal and digital. So we call it high-speed digital because there is lots of advanced digital circuit design aspects, but there is also stuff like that you may put into the context of mixed signal. So I would say the chapter about PLLs and time-to-digital converters is more related to mixed signal. Then you can see there is also high-speed arithmetics, design of latches and flip-flops, memories. This is more related to digital design. So I would be also very happy to see you guys in this course. I guess it's also on Monday morning. So this is also a feedback of you guys. Well, Monday morning is a tough time for us to show up. Yes, I know I have to apologize, but this is somehow related to the fact that I work full-time in industry, and it's hard for me to show up here in the middle of the day. So it's easier to convince my management that I can give this course here if it is in the morning and does not cost a full day. So that's the reason for it. I hope you can make it anyhow and visit us in one of these courses, either this one or of course also this one. Okay, thanks a lot for attending. Sorry, Michael, that I stole so much of your time for the tutorials. All the best for the exams. I guess we made a fair offer. Okay, it has to be an exam, so we cannot give it away for free, but I believe that we also tried not to dive too deep into the details, and I also tried to sometimes give hints what is important, what is less important, what you should have a look. For instance, even today I emphasized some stuff, and all the best for you guys. Thank you. Bye.